lecture, we're going to be doing some pedigree analysis, and I'm going to orient you to the pedigree again, and hopefully at the end of this will all make sense, and you can use these familial relationships to figure out what people's genotypes are and do some other interesting stuff, which we'll probably get to later, like figuring out what are the odds of that person passing a particular trait on to their kids. So there are sort of four possibilities when it comes to a pedigree or when it comes to a trait. Is the trait dominant or recessive? So when I say dominant or recessive, what I mean by that is if you have one copy of the dominant allele, you will wind up with the condition if it is dominant. If the condition is recessive, like we've talked about pretty extensively, but if the condition is recessive, you need to have two copies of the recessive allele to get it. The other possibilities are, and something, by the way, can be X-linked and dominant, or autosomal and dominant, or something can be X-linked and recessive, or autosomal and recessive. But the next thing is whether it's X-linked or autosomal. So X-linked are those X and Y chromosomes. Those are those sex-determining chromosomes. And the other chromosomes are your autosomal chromosomes, or your non-sex-linked chromosomes. So you have 44 of these, because you're a human, so you have 46 chromosomes. Or people in general have 46 chromosomes, I should say. So you have 44 autosomal chromosomes, and you have 2 X-linked chromosomes. And we're going to talk about determining whether or not things are X-linked or autosomal, dominant or recessive. So, does everyone with the condition have an affected parent? So if you have this condition, does your parent also have it? If the answer to that question is yes, it is likely a dominant trait. It's not for sure a dominant trait, it's just likely a dominant trait. If you have a condition and your parent doesn't have it, then it is recessive. And I would say likely recessive, but it's recessive. There are certain things going on called like penetrance and stuff like that, where you can wind up with an allele but not have a condition. But all of the things that we're going to study, if you have it and your parent doesn't have it, it is recessive. So as a generalization, if you have it and your parent doesn't have it, it's a recessive condition. So X-linked or autosomal, this is talking about, is this on the sex chromosomes, or is this going to be on one of the other 44 autosomal chromosomes? If it affects mostly males, then it is likely X-linked. And there are a few other things you can think about, like whether it is dominant or recessive. If it's dominant and dad has the condition, then all of his daughters should have it, because he only has one X to give away, and he's going to give that X to any daughter that he has. So if it's autosomal, or if it's sex-linked or X-linked dominant and dad has it, all of his daughters should have it. But if it's dominant and only dad has it, then none of his sons should have it, because he's not giving that X to his sons. He's only giving that Y to his sons. Anyway, I think probably the best way to go about doing these things is to just kind of look at a pedigree for a few minutes and think about it. There is kind of a flow chart that you can use, and if anybody wants to be highly analytical like that, we can talk about that in class this week. But let's look at this, and there's more to this. This is just generation 1 and generation 2. But let me orient you to this here really quick. So circles are females, squares are males. Okay, if the shape is filled in, then the person has the condition. So if the shape is filled in, the person has the condition. This line right here represents what's called a marriage line. So these people, and they had kids. It doesn't necessarily mean that they were married. That's just what they call it. Individual 1 and 2 had kids. This line represents a sibling line. So anyone who's connected to this line is a sibling of everyone else on this line. All right, and you can see some of this second generation have gotten married, and we'll see in a minute they did have kids. So this Roman numeral 1 over here on the left represents the first generation that you're looking at. Roman numeral 2 represents the second generation. So if I was talking about individual 1-2, I would be talking about the mom of the first generation. If I wanted to talk about, say, this individual here, I would say individual 2-4. And this is an unaffected female who is married in the second generation. And you see here, these people that are not on the sibling line are just people that married in from some other family. They're not related to this family. They've married in. So marriage line here, sibling line here. Squares are males, circles are females. If it's filled in, the person has the condition. The Roman numerals represent the generations, and the numbers represent the individuals in each generation. So, do we think this is an autosomal? I'm sorry. Do we think this is a dominant or a recessive trait? It looks like a dominant trait to me. Definitely looks like a dominant trait. It's not necessarily the case, but you can see here this boy has it, this girl has it, and their parent also had it. What are the conditions under which it could be a recessive trait? Well, that means that dad here would have to be heterozygous. If this was a recessive trait, dad would have to be heterozygous because he's not displaying the trait, but he'd have to have a small allele. But let's look at the next generation, and maybe we can figure something out from that. Okay. So it still looks like a dominant condition to me. There's no guarantee of that, by the way. It could certainly still be recessive, but it looks like it's dominant to me. And it looks like this male has passed on this gene to both of his children, and this female has passed on the gene to one of her sons. So you're not seeing that typical skipping of generation step that you see with the recessive trait. And the next question that we should ask ourselves is this an X-linked or is this an autosomal trait? To me, this looks pretty autosomal because females and males are both being affected. So if you had to ask me about this pedigree, I would call this an autosomal dominant condition that's passing through this family. This is probably an autosomal dominant condition. And you can figure some stuff out beyond that in terms of likely genotypes. It's easier if it's recessive, but you know for a fact that anyone that does not have the condition is homozygous recessive, right? Because if they were heterozygous and it's dominant, or if they were homozygous dominant, obviously they would have it. But so anyone that has an open circle is homozygous recessive. So I see here that there's one affected individual, one affected male on the sibling line. And you'll also notice that neither parent has the condition. So it's safe to say that this is an autosomal. No, it's not autosomal. Sorry, it's not safe to say it's autosomal. But it's safe to say that this is a recessive condition. Because the only way for this individual to get it, if it was dominant, one of these parents would have had it. They'd had to have one of those capital letters in their genotype. But since this individual has it and neither parent has it, I would call this a recessive condition. So let's look at the next generation. This is definitely recessive. And we can kind of start figuring out what people's genotypes are So I can say with some certainty that both parents are heterozygous, both like 1-1 and 1-2 are heterozygous because they've passed this gene on to their offspring. And you can also, they passed on one recessive allele to their daughter. So her her chromosomes have one recessive allele because her son wound up getting this. All right, so let's look at the final generation here. And this kid got it, so this looks to me like it is a X-linked recessive condition. So it's X-linked. The first thing that makes me think it's X-linked is that only these boys are getting it, only the squares are having the condition. That is not a guarantee that it's X-linked, but it's certainly an indication. So I suspect that it is X-linked because, again, only guys are getting the condition, and you'll remember that women have that extra X chromosome to compensate. So even if they wind up with one copy of the allele that would give them the condition, they have the other X that they can use to compensate for it. So, just looking at this, seeing that the first generation doesn't have it, but the second generation does, it's definitely a recessive condition. And just looking here, it does appear to be X-linked, right? And you can figure out the genotypes of most of the people in this pedigree, at least the related ones, just by looking at this. So I would say grandpa up here not probably, but definitely has a normal X, if you assume that this is an X-linked condition, is a normal X and is normal Y. And then grandma up here has a recessive X. She has an X that gives the condition, and then she has a normal X. And you know that because she doesn't have the condition. She doesn't have the condition at all. And so these two, dad up here passed on his normal Y chromosome to his son, and then grandma passed on her trait, her X chromosome with the condition to her son.